This video is presented to you by Physics for Students.
Okay, so the topic for this video particularly is torus homeomorphic to the circle would be, we would first like to know what is a torus, then we would see what is a circle, and this is something which we are going to explain a little bit, which is called Lebesgue covering dimension. And what is the proof for this particular question, is torus homeomorphic to the circle. So it would be a kind of a very short video in which I would be trying to explain to you the basic reason, and I would like to stick it to the as simple and as basic as I can. So coming to the immediate question, is torus homeomorphic to a circle or not? The answer would be yes. It is a nod of the head, which means that it would be no. Okay, so this is basically what we know, that a torus is not homeomorphic to a circle, and we would go together and we will try to explain the proof for this particular question, and we would see that how these proofs can be elucidated in a mathematical or as well as in an intuitive manner. So my approach would be, if I take the proof, then first what I would like to do is that I will show you a mathematical proof. Then I would like to show you a simple proof, which is just a kind of an intuitive understanding for the proof. Then I would like to go for a proof through for the fundamental group. I assume that the viewers know in topology what is a fundamental group. And then I will prove the same thing through Lebesgue covering dimension. So these are the fourfold approach. I would say fourfold approaches that I would be taking forward in this video. The basic reason behind is that to make you all aware about the mathematical part and a simple and yet an intuitive approach for this particular question. Now, torus, as you see, is something which is, always seen in topology and mathematics, and all these pictures that you see in general always cover up a torus. So this particular proof revolves around torus, but torus appears naturally in various mathematical contexts, pictures in internet when you search and you look over the topology videos. Now, torus is the only surface which is covered by the plane, and hence it is supported by a Riemannian metric. So tori, I would say, which is a plural of torus, supports with multiple holes, support a hyperbolic, or which you can call an intuitive approach as a negatively curved matrix. So in general, this is the reason that we have taken up torus and why torus has emerged to be very important. Now what I would like to show you are the basic features of a torus, right? So topologically, a torus can be defined as a closed surface, right? It is in topology, this topological torus is also, it is called the product of circles. Okay, so also it is known, this topological torus is also called as an Clifford torus. Okay, Clifford torus, which is named after this mathematician as well as philosopher, William Kingford Clifford. I think you are aware about Clifford algebra and Clifford torus, so everything owes to this great man. English mathematician, philosopher of mathematics also, William Kingdon Clifford. Right. Now a torus can be made by revolving a small circle, which you see on the right hand side of the screen in blue, with small r around a line with a bigger circle, which is this big R. Obviously it has got no edges or vertices. It is not a polyhedron, and yes, so the surface area is given by this. So these are more or less the fundamental features of a torus, although there are many things which comprises of torus, but it is just a basic, to start with, the basic features of a torus. Now the fundamental group of torus. The fundamental group of the torus is just the direct product of the fundamental group of the circle with itself, which is something like this. Okay, so I have followed the standard notation. Okay, I have taken S1 as the circle and the bold T as the torus, and it can be called, it is a direct product, so it's a direct product of the circle itself. So also it is important to note that the fundamental group of the circle, if I tell, is this one, and the fundamental group of circle is isomorphic to Z, which is, you know what it is, Z is isomorphic to that. It is a set of integers, right? Now the torus also has a generalization in higher dimensions. Okay, the n-dimensional torus, or n torus as we call it, we discussed earlier that a torus is a product space of two circles. Hence the n-dimensional torus is a product of n circles, which is something like this. Right, so we can take it, we won't take it right at this moment, but this is just a kind of a definition which would give you an understanding that if we call it as an n-dimensional torus, how it would look like. Okay, so what we do is that we come to the mathematical part of the proof. Okay, so we are now heading towards the mathematical part, which is the first part in which we are going to see certain mathematics, and we will prove that. So if we take ahead from this, that we can write it is a product of two circles, we can write it in this way. Okay, and if I take, say for example, now after this writing these as the product of two circles, what I can do is that I can take a step back. Okay, I can step back, and I have taken two examples, right? X and T and Y and V, just in random, are the two topological spaces. And if this is a kind of a function which maps, and it is a bijective function, then what we can say that F is said to be homeomorphism, or rather I would say homeomorphic. And if F is continuous, obviously the inverse of F is also continuous. So in that case, we can write it in this way: X comma T is homeomorphic to Y comma V, or simply X is homeomorphic or homeomorphism to Y. This is once we take the context of topology. Now if you are seeing these equations a little bit hazy on the screen, my kind apologies for that, because my system is not working right at this moment. I have to use another kind of a tool to get these equations done. So this is a step back in which, why I'm doing it, I will just explain you. This is because if the topologies are understood from the context, how we write the notation of homeomorphism, which is X, which is homeomorphic to Y. Now taking ahead from this, what we can do is that we can write this, right? This one. Further, what we can do is that we can write this, right? So this is equals to Z. I think things are quite clear. So this equals to this, and also this equals to Z multiplied by Z. Since this pi underscore 1, it preserves the products. Hence, what we can say, that torus is not homeomorphic to the circle. And why? Because since the homeomorphic spaces have the same homotopic group, and they don't do, so it lies as it is not homeomorphic. So if the viewers want to take a kind of a note on the mathematical part, you can do that. But this is a very kind of a simple approach why torus is not homeomorphic to the circle, because the homeomorphic spaces have the same homotopic group. So this is why, and we have just deduced it. So those who are not quite into the mathematical part, just hang on, because I will be coming up with a much more simpler and an intuitive approach for this proof. Now, there is another way in which we can do, right? This is the mathematical way. Let us see if in a geometrical and a visual way we can do that. So if I take S is, this is a circle, and these two red points which are pointing these two things, and I remove them, right? So you see on the next circle, which is the figure, I have removed this. So if I disconnect, I would say that this the circle is disconnected by removing those two distinct points. So what we get is what we call a disconnected topology, right? So we just randomly erase those 2 points from the circle, and we get a disconnected topology. But what we do if we want to remove this, we cannot, right? So removing any 2 points from the torus, which is on the right hand side of the screen, it actually never disconnects it. So we do not, what I would say, kind of get of a disconnected topology. So this is a disconnected topology, and this is not a disconnected topology. I think this also clears up the concept. Okay, so we are going back to another proof, which is the second one, which I would call is the fundamental group, how we use the fundamental group. Now, I told you that I assume that people know, the viewers know what is a fundamental group. Okay, the fundamental group of torus is given by this. So if we can go further, we can write up to the n torus, which I told you as an n-dimensional torus. We can write Zn. Now, in other words, what we can tell is this. So T2 equals to the product of those the two circles, and the fundamental group of torus is isomorphic to this. Right. So what we are using the fundamental group. So just hang on and you can watch how it happens. However, on the other hand, the fundamental group of circle is given by this, right? This one. And we can write this as isomorphic, right? But yes, the fundamental group is this one is isomorphic to Z. But you should remember one thing, that Z to the power 2, or I can call it Z square, is not cyclic as per the definition, but Z indeed is cyclic. Hence, we can tell that they are not homeomorphic, and we write it in this way. So this is another kind of a proof in which we have used the fundamental group of circle and the fundamental group of torus, and we have shown that they are not homeomorphic. How? This is how it happens. Now these are some fundamental group of some common spaces: circle, complex projective space, and torus, real projective plane, sphere, and figure 8. I have deliberately skipped over Klein bottle. So these are basically the fundamental group of some common spaces, and this one actually shows the fundamental group. H1 is the first integral homotopic group. The cross shows the group direct product. This one is the free product. The bold Z as a ring of integers, and this one would be a cyclic group of order n. So this is just a kind of a recap, nothing to worry about. This is just if you want to take a note and really want to know what are the fundamental group of some common spaces. Okay. So we come to the last part of our video, that how we can prove this with Lebesgue covering dimension. Now, I would just like to tell you that Henri Léon Lebesgue was actually a French mathematician whose generalization basically of what we call the Riemann integral revolutionized the entire field of integration. I am not going to tell you much about what was the integration all about, the vertical integration, etc. But just try to understand that it actually was a generalization of integration, right? As I told you earlier in the video of topology, also from Euclid we are going to metric and then to topology. From Einstein, from Newtonian mechanics we are moving to special and then to general theory of relativity. All these are because we are trying to make things much easier. So the generalization actually occurs in every part of mathematics and science. I think every part of human life actually. So towards the end of the 19th century, mathematical analysis was limited to continuous functions, right? So the Riemann method of integration was applicable only to continuous, or you can say a few discontinuous function. Lebesgue actually formulated a new theory of measure and formed a new definition of the definite integral. In measure theory, actually Lebesgue measure is considered to be the standard way of assigning a measure of subsets of n-dimensional Euclidean space. Now I'm not going to explain all those, it will become clear. What we are particularly interested is what is called Lebesgue covering dimension. I have just noted the major achievements of Henri Léon Lebesgue. So let us take and understand what is actually Lebesgue covering dimension. Okay, so if we want to go for a very technical definition, then what we can call is that Lebesgue covering dimension of a topological space is one of several ways of defining the topological space in an invariant way. Okay, now let us go to the roots. Let us understand what does actually it means. Okay, so we are thinking that, for example, whenever we think of anything, the basic notion which comes into our mind is the size, right? Size of any object, size of anything, right? Now, the simplest way to think about is that when we start with things like, for example, the length of a line, okay, the volume of a cube, and the area of a square, right? So simplest thing is that we start with things which have a common notion called size, and then we go ahead and measure. But just note one very subtle thing in all those measurements. What we are doing is that we are all trying to find the product of their lengths. So more or less what you can see, all those three examples given over there, they're nothing but the product of their length, right? Now, say for example, we are thinking that what if we don't want to measure in terms of the product of their length? What if we want to extend the idea of size to any size, if you want to extend the shape to any shape? So again, what you see is that it is a kind of a generalization that we are talking about. Can we do that? So that is basically the idea of Lebesgue dimension, so that we are not restricted to a particular space or an object which has certain dimensions. So for example, this line and all those objects which you see are there's a kind of a finite regular polygons, right? And if we want to extend it to something weird like this, right? These are all topological shapes which is taken. So we take what we know and we just cover the extra one with cubes, again divided into very small cubes and things like that. So the basic idea is to provide a number that describes the space and doesn't change as the space continuously deforms. Obviously deformation is there. Without deformation we cannot get a topology. So but we want to get a number that describes the space and it doesn't change as the space continuously deforms, and that is why we call this as something which is invariant under continuous homeomorphism. So something which would be totally invariant. So I think you can now think a little bit back, and if you see my tensor analysis video, you will see there I have also shown that the regarding the vectors and the bases of vectors, how do they change, what remains invariant, etc. So in a similar way, we are trying to describe a number that is invariant under the changes and under the movement of homeomorphism. So this is something which is important. The conventional idea of measure, how do we do that? That's why I have kept an icon of a telephone which is quite old aged. Size of various sets such that the combining disjoint sets make their sizes to add up. So what I mean to send is this, and the new one would be, or the modern one thinking would be, sets do not change size when you shift them by some amount in some direction. So the conventional idea of measure, and then we come to the modern idea of measure, which is the Lebesgue dimension, that the sets do not change when you shift them in some amount. So the generalization of the familiar notion of length, area, volume, ... to figures which might have no length, area, no volume, obviously in the classical sense, which we call length, area, and which is not. So that is basically the contribution of Henri Lebesgue. So in Euclidean space, I just taken a triangle to demonstrate that in ordinary Euclidean spaces, 0 goes for lines for Lebesgue dimension, 1 is for 0 for points, 1 for lines, and 2 for planes, right? So just getting a kind of a general idea what Lebesgue dimension and what would be the impact of Lebesgue dimension in topology, so that we are moving from the conventional way of measuring things into something which doesn't have a volume at all in a classical sense. So the Lebesgue covering the dimension of an informal definition, we can do it in this way, that a topological space, say for example, this would be a rigorous definition, can be covered by open sets, right? In that one can find a collection of open sets such that X, right, a topological space which we define, lies inside their union. The covering dimension is the smallest number, say for example n, such that for every cover there is what we call a refinement in which every x lies in the intersection of not more than n plus 1. So that is more or less what we can call, it is an kind of a what we call informal definition of Lebesgue dimension. But note one thing, that it is not more than n plus 1. That means we are restricting the measurement in terms of not going. So we are trying to get in a number which is topologically invariant. Now, for example, these words, doesn't it make a little bit more confusing? Okay, so let us see this. So see, on the left hand side, this diagram shows a refinement of a cover, and on the right hand side, this arrow shows on the circular line. Note, I will just try to make a note that the refinement of no point in the line is contained in more than two sets. Okay, and you can see how the sets links to each other and they form a chain. I have taken this from Wikipedia, so this is a kind of a geometric understanding of what actually Lebesgue dimension looks like. Now you might be thinking that whether it is just an intuitive understanding, all those words, etc. No, we are not going to hold for an intuitive understanding. The n-dimensional Lebesgue measure which we are into is actually what you get from a set of rules. Just quickly go browse through the rules. This is actually a partially defined operator which assigns a value in R to some functions which goes from n to r. I don't need to explain. I think things are quite clear. What we call them are integrable functions, right? And we assign them certain values which are called the total integral, right? And if an integral function is everywhere this, that is greater than equal to 0, then the integral is also greater than equal to 0. The space of integrable functions is closed under linear combination, and f, which is a function, is a linear operator. If f is the countable sequence of this one, f0, f1, f2, ... where everywhere it is greater than equal to 0, then this is the actually to the extent that this converges, where f converges, and f becomes non-integrable, right? And another most important point is that translating a function does not affect its integral. Now this is very, very important. When we translate a function, it is not affecting its integral. That means what I showed you earlier, that we are trying to get something, some number which is invariant, which doesn't change with the change in topology. And the unit cube has a measure of 1. So that is kind of a mathematical plus intuitive understanding on what is Lebesgue dimension. Okay, so we are going back to the proof, which is the last part of this video. We are going to take forward Lebesgue dimension, and let us see. Now, one important part of Lebesgue covering dimension is this: homeomorphic spaces have the same covering dimension, and the covering dimension is topologically invariant. Among the many other properties of Lebesgue covering dimension, this is one of the important property, that homeomorphic spaces have the same covering dimension. Now the question what we have found is that if homeomorphic spaces have the same covering dimension, then do the circle and the torus have the same covering dimension? This is the question which we are taking out from Lebesgue covering dimension and trying to answer. And obviously it is a no, because the Lebesgue covering dimension of circle S1 is 1, and you see the Lebesgue covering dimension of the torus is 2. So I think that you got this point. Like I mean to say, how the Lebesgue covering dimension, what is Lebesgue covering dimension, what is something, a product which would stay invariant with the change in the function, and how the Lebesgue covering dimension of circle and the torus are different. So now what we can say is this: a circle is not homeomorphic to a torus, and we write it in this way. Okay, so I think that it is it is now quite clear to you, the viewers. If you have any question, you can put it up in the comment box of my YouTube video. So this is these are the ways in which I try to prove it. One is a mathematical approach, taking the topology. Second is a kind of an intuitive approach. Third one is using the Lebesgue covering dimension. So all this actually, and how Lebesgue covering dimension is related, and why we want a topologically invariant number. So I think that actually covers the entire video. I would again extend my sincere thanks to Dr. Richard Sott for clearing up certain concepts on me for topology, and he is one of the, for me, I have known one of the best topology teachers working with IES New Jersey, a retired professor. So I think that's it. So we are done with today's video, and the next video which are coming up is the common terms which are used in topology. I would like to illustrate them. What are the common terms which are used in topology, and also with the meaning, obviously. So that would be the context of my next video. I think you like this video, so subscribe and please press on the bell icon so that you get all the notifications from Physics for Students. And also do put up some comments. You can email me also if you have anything that you want to know or for further clarification, because videos always do not make things clear, so you might have something in mind. So do let me know, and I would see you soon with the next topic in topology. I hope you are quite okay with the series, and wish you all the best, and stay happy, stay safe, and goodbye.